So we last left off with example 22.7. So we did, and this is for PHY 112. And we're looking at magnetism. So we kind of want to figure out a few things in the next. Okay, so we were doing example 22.7, but what is it that we're really talking about? We're talking about how to get a magnetic field from a current. So let's say we have current coming in, we've got this perfect circle, and then current going out. And the circle has some radius r. We found that when we have that situation, we have a B field created that is mu naught I over 2 times the radius. And let's remember what mu naught is equal to. Mu naught is equal to 4 pi times 10 to the minus 7. And what are the units on that? They have to be meters. Oh boy. In the end, we're going to end up with Tesla meters per amp. So Tesla meters per amp. Okay, good. Of course, the current I, whatever it is, will be given, and the radius will be given, so that all we really need to know is what is the direction of this current. What is the direction of the field if the current is flowing like this? So you can just put your thumb in this direction of your right hand. So we're going to use the right hand rule. Here's our thumb along the current going north like that, or going up the page. And you curl your fingers. If you've got your thumb going that way, your fingers curl this way and then point up back at you. So the field then for each point along this is going to be inside, it's going to go up, right? It's outside that the field goes down into the page. Okay. So that's what our B field looks like. It's more uniform on the inside than the outside. The inside actually has a fairly uniform B field, and the more loops you have, the more uniform it is. And let's look at when you have a solenoid, which just means a solenoid means, whoa, what happened there? A solenoid means many loops. And when we do that, we get that our B field is equal to our mu naught times the number of loops per unit length. So that's our number of loops per unit length times the current. And that's what our B field ends up being. So this is for a solenoid. Okay. So that was just a little refresher to get us back into the game a little bit. What we're going to look at now is let's just get rid of all that. We're going to look at two conducting wires, and they're running completely parallel to each other. And their currents is initially going to go in the same direction. The reason we call the distance between them R is because if you think about just one of the wires, okay, here's wire 1, here's wire 2. If you think about just one of the wires with its current going north, up on the page. Okay, so its current is going this direction. The B field that is made is going to be detected a certain radius away from the current, right? And if you put your thumb in this direction and you curl your fingers around, your fingers curl down into the page, okay? And that's why I drew the B field into the page at that point for current 1. If we were to look at current 2, so that's current 1, if we were to look at current 2 and we put our thumb in that same direction and we come over to where the wire is, we would notice that that would be the B field from 2, and this is the B field from 1. Okay? So it would be out of the page for 2, into the page for 1. So, but we're only going to look at one at a time. So what we really want to do is look at we really want to look at the B field according to 1. Oh, I have it totally backwards. You guys are probably yelling at me. Of course, this one is out of the page. And this one is into the page. Crazy. I was using my symbols backwards. Okay, so let's do it. This means out of the page. And this means into the page. All right, just to clarify for me, keep me straight. Okay, so what do we want to do? We want to figure out the force. So we are after, right now, we want the force that comes from these two wires with current flowing in them. Okay, that's our thing. That's what we want to know. So, the Lorentz force equation is going to give us what we need. So let's look at the Lorentz force equation. And that is F equals Q times the velocity of the charge times the B field that it's in times the sine of theta. Okay, well, let's do this thing where we create a length from, oh boy, we create a length from here to here, say. We call it L. Okay, and that L corresponds to both conducting wires. Okay, so our velocity would be then the length L divided by the time that it takes to get through across L, because V equals our distance over time. So that's going to equal our length over time. And we can rewrite this then as Q times length divided by time. I have to fix my notes for a second here. Okay, Q equals, V equals length divided by time. And there's our B sine theta. And instead of having length divided by time, if we put the charge divided by time, then we end up with the current. Charge over time is your current. So the current times the length times B times sine of theta is equal to our force. So we've got our current, we've got our length of the current, we've got our B sine theta. Okay, so we can go with that. And when we apply it to this situation, we want the force of 1 onto 2. Okay? So we've got this length of wire. We've got the current of 2 times the B field from 1. And then we're going to multiply by the sine of theta. But the sine of theta, everything's perpendicular to each other. So theta is equal to 90 degrees, making this equal to 1. So we're good there, and we can now just come down. We can add a little something. So we want the force. We're dealing with the force now. And instead of taking up all this room with these terribly written words, let's erase them. And use the fact that our B field is equal to mu naught I1 over 2 pi r. Okay, now where did we get that from? We got that from last lecture, where we said all of these different things have, all the different scenarios have different equations that go with them. And the equation for the B field around a wire, a straight wire, is this. Okay, so that's the equation for a straight wire. Let's just say okay. So if we take this equation here, because we've realized that this is equal to 1, and we insert our B1 there, then we have F12 is equal to our length times I2 times I1 times mu naught, and we're going to divide that by 2 pi r, where r is the radius away from, that 2 is away from 1. Okay, that's this radius r. Okay. So that's a great, it's a great equation to work with, and we can then say, of course, the force of 2 on 1 is equal to minus that, using Newton's law, Newton's third law. But if we are just looking to call those forces some magnitude F, then of course we get F is equal to, in fact, let's do F over L. So it's the force per length. So I've just taken this L and moved it underneath. And that force then is equal to mu naught I1, I2 okay, I1 and I2 divided by 2 pi r. And then to keep things in general, we're going to add the sine of theta. So the force per unit length, so technically these two wires are infinite, okay? The length of the wires is infinity. All right? We're only taking a small subsection length and that's our force per length. Okay, so we could call it a meter. We could have it a force per unit length, make it a meter. But this is the equation that tells you the force per unit length for two current carrying wires a distance r away from each other. Okay. So here's where we get, I'm going to rewrite this. Force per unit length is equal to mu naught I1 I2 over 2 pi r. Here's our two current carrying wires. There's R, there's 1 and there's 2, and we can call it I1 and I2. Okay, so that's just to remind us what we're dealing with here. So here's the thing that I kind of was leading to in the last lecture, but here is what we call the operational definition of an amp, an ampere, which is basically an amp. Okay, the unit. So this is the operational definition of an amp. Okay, it's based on this very thing. Okay, so if we set R equal to exactly 1 meter, 1.0 meters, 1.00000 meters, and we say that the current is equal to 1 amp, that's I1 and I2. Then our force per distance is equal to 4 pi times 10 to the minus 7 Teslas times our 1 amp times our other amp, and we're going to divide by 2 pi times 1 meter. And when you do this, the pi's cancel. 4 divided by 2 is 2. So you're left with 2 times 10 to the negative 7 newtons per meter. Okay, and it should be newtons up here, meter down here. So it should be newtons per meter, and that's what it is. But look, this right here is how we know when we have a force between two wires. So here's what really happens. They have the two wires, and they are attracted to each other by this force. Okay. There's F21 and there's F12. And that force per length must be 2 times 10 to the minus 7 newtons per meter. And that defines the current to be exactly 1 amp. So I equals 1 amp. And that's I2, and you have 1 amp for I1 as well. So that's how we define an amp. You say, okay, it's 1 amp if this force between them is 2 times 10 to the minus 7 newtons per meter. Okay. So that's also where that definition of mu naught comes from. Mu naught equal to the 4 pi times 10 to the minus 7. It has to be 4 pi because when you divide the 4 pi by 2 pi, you get the 2, right? And that's what we need. So this mu naught in Tesla meters per amp, that mu naught comes from this this definition. So this is experimentally defined. Okay. So far, so good. All right, so we've explained a few things. We've covered sections 9 and 10 just now. Between the last lecture and this lecture. But we skipped over 22.6 through 22.8. And we haven't touched on, so we have left to do these sections plus 22.11 because we did 9 and 10 after 5. And I'm not sure why they would have done it any other way because we need those things, but I don't know. Don't ask me. So here we go. We're going to talk about section 22.6, which is the Hall effect. Okay, so the Hall effect. We're going to talk about it. So, okay, I don't know a better way to do it than to just say what happens here. So this is a wire. Okay, we're zoomed in on a conducting wire, and we use width normally for a conducting wire's width, but we're going to use length, L, for the conducting wire's width. And the reason we're using length is because what's going to happen is, let's say we've got, all right, we've got electrons, okay? This little guy is going to be going this direction with a velocity, drift velocity, which means the current goes this direction. And so that's happening. And we also are doing this all in a B field that is coming out of the page. So we're going to fill this page up with a bunch of E field. And let's do some right down the middle. So it's uniform. We know that it's a uniform B field. Okay. So what happens? You've got the three things. You've got your current I. You've got your perpendicular B field. Then you have the force that is generated. And they're all perpendicular to each other. Okay? We've got our current going in that direction. Our B field is shooting up out of the page. And then the force, of course, would be in this direction. So, okay, that's how we've drawn it. That's how we've got it. Okay, so our force is forcing this guy. So here it is, an electric charge going to the left, but it's forced because of the magnetic field that it's traveling through. It's forced to go down. So its path, if there was another guy right here, a little guy right here, its path kind of goes like this. Okay, because it can only get so far, right, to the bottom. But this force, you could think of as an EMF. If we were to put an E field, positive and negative, we'd have an EMF that is pushing in that direction. Okay? So it tends to want to make, well, let's just write it out. The net effect of the Hall effect is to push charges to one side of the conductor. Now, what if we're talking about a positive charge and the current is still going in that direction? So the current's still going this direction. A positive charge just has a drift velocity that also goes in that direction. So that's VD positive. Here's VD negative. Everyone wants to get the test that says they're VD negative. And here's our negative. Okay. So we got our positive, we got our negative. Well, the same thing happens. It's still the same B field. It's still the same current. it's still the same force. So if it's a positive charge going in the other direction, a hole or whatever you want to think of it. Maybe it's, I don't know, maybe it's a loose hydrogen proton, right? Going in the other direction. It also has a force that forces it down. And those positive charges, let's draw one here. Let's call it a proton. And it's going to go that way. Okay? It's got its force pushing it down and its other force pushing it to the right. So all the charges in this situation want to stack up at the bottom. Okay? All right. So eventually, did I say it was an EMF? Yeah. Okay, so we have this Hall EMF. Let's call it Hall. Okay. Eventually, the charges that are going to stack up at the bottom, the electromagnetic force, QE, is going to equal our magnetic field situation with our drift velocity and our magnetic field, such that we can say QE equals QVDB. And this is our Hall EMF. I'm sorry, our E Hall. But that's equal to our EMF per length. So our Hall EMF per length, which isn't the length. It's not this, okay? That's not the length we're talking about, okay? We're talking about the width, actually. And the length is purely the distance that this charge can go to the other side. That's all, okay? It can only charge, it can only go from one side of the conductor to the other. So that's this length. Okay. Since we've got that, we've got this equation, we're going to cancel our Q's. We're going to say that the EMF of the Hall is equal to the length, or I'm sorry, the width, actually the length of travel, but it's really the width of the wire times our drift velocity times the B field that they're sitting in. And this, my friend, is the Hall EMF. That's how you figure out your Hall EMF. So you need to know L, which is the width of the conductor. You need to know V, the velocity of drift. Drift velocity. And you need to know the magnetic field that it's sitting in. Okay, one more equation for our stuff, for all of our power. Okay, our powerful peoples. What if we wanted to solve this equation for the drift velocity? So we can, and if we're given the Hall EMF, and we divide that by the width of the wire and the B field, then we'll have the drift velocity straight up drift velocity. Okay, so why am I pointing out the drift velocity? Well, here's why. If you have blood vessels in your body, and I hope you do, so here's these blood vessels, and you've got blood flowing. Is this blood colored? I think this is green. All right, well, you've got green blood. Is this green? Hard to say. Okay, whatever. This blood is going through your vessel. If there are charged ions in there, so let's say we've got sodium chloride, NaCl. Okay, but some of those are positive and some of them are negative. I can't remember which. Sodium's negative and chlorine's positive. So what if you have just the sodium, and if I have it wrong, forgive me, but let's say we've got a negative sodium ion. So it's technically a massive atom with an extra electron charge, okay? And that extra electron charge is flowing through here, and we set up a B field. So we set up a B field over this blood vessel, and we don't want that. We want this. So here's our B field. And we detect a Hall EMF going from one side of the vessel to the other. So there's a Hall EMF. These guys are perpendicular to each other. It's all perpendicular. Everybody's 90 degrees from each other. We know this L length, the distance from here to here is just the diameter. So L equals diameter of vessel. And we can then find this drift velocity for the Na ion. So maybe let's do it. Maybe let's do it. This is example 22.3. And I'm not altering this one at all, okay? We know that the blood velocity is 0.2 meters per second. Okay, that's our drift velocity. The diameter of the vessel that is 4 millimeters, but we're going to write that as 4 meters. We put B equal to 0.1 Teslas around the whole thing. And you could do it from one side of your arm to the other, right? So if you're testing the blood flow in an arm, you can immerse the whole arm in the B field and then just do your Hall test on it. We do all this stuff, and we want to know what is the Hall EMF. So we'll go back to our equation, this equation, and we'll say that the Hall EMF is equal to our length times our drift velocity times our magnetic field. So this shouldn't be terribly difficult. 0.1. We're going to multiply that by 0.004, and we're going to multiply that by 0.2, and that should all be in volts in the end. This is 10 to the minus 1. 4 times 2 is 8. This would be 10 to the minus 3. 1, 2, 3. And this one is 10 to the minus 1. And it's all still volts. So we've got 8 times 10 to the minus 5 volts. That's our Hall EMF. Okay, I like it when it works out like that. If you wanted to call that something that was, all right, so I don't know if you guys have noticed, but we do it in steps of 3. The significant, or the steps of 3 for the metric system, not SI metric. So let's start with 1. It would be whatever the unit is. So I'll just put a box here. If you go to 1,000, it's kilo whatever. So that's 10 to the 3. 10 to the 6th is mega whatever. 10 to the minus 3 is milli. 10 to the minus 6 is micro. 10 to the minus 9 is nano. 10 to the minus 12. Boy. Why can I remember 10 to the minus 15? I can remember 10 to the minus 15 is femto. I can't remember 10 to the minus 12. Well, there I am. failing. So look here, micro, 10 to the minus 6. We're at 10 to the minus 5. So we can divide by 10 and multiply by 10. So here's us multiplying by 10. Here's us dividing by 10. And there's our volts. So our E Hall is equal to 80 microvolts. Okay? Good. Femto whatevers. Femto whatevers. Okay, so. All right. We've got another situation that we can analyze. And you should really look at figure 22.30. Hopefully I'll do it some justice here. We've got this square. It's a perfectly good square. We've got our negative side, our positive side generating an EMF. Of course, that means that there's a current that's going to flow this direction. Let's say that we put an overall B field on this thing. All right, let's draw our B field in blue. But we only do it over a certain little range. But we do it on both sides. Okay, the range that we're doing it over is L. So L is equal on both sides. Our B field's going up. Our current's going to the right. So you do that right-hand rule thing. So we've got our current going this way, our B field going this way. That means that the force has to go, do your thing where you put your current, your B field, your force. The force ends up being right-hand rule. So should do this. Okay, so that's the direction of our force. So let's put the force in green. The force on that wire is going to be up. But now let's look at the bottom where our current is going this direction. And we'll analyze that. So here, down here, we've got our current. I didn't want to do that in that color. Okay, we've got our current. That's our current, this is our B field, and then that's our force. So we've got our current, we've got our B field, and that means that our force is actually going to go into the page, okay? Because we're flipping that diagram. We flipped it and put it here. In order to do that flip, this goes into the page. So our force is going to go into the page for this side. What if we have this whole thing on an axis that can spin? So we've got out of the page at the bottom, into the page at the top. That means that the force is going to want to go like that, spinning this thing around. That's what we're getting at. But first we want to know what is the force that that's driving it. Well, we've already seen it. The force is equal to the length, our length L, times the current, times the B field, times the sine of the angle between the current and the B field. So it's the sine of the angle between this and this. And we already know that that is 90 degrees, so our sine is going to equal to 1 in this situation. This is in general, okay? But in our situation, our force is going to be equal to L times I times B. Okay. We're going to do an example. And when I get done with this example, we will continue with another video after that. Okay, so let's do an example of this. What is the force on a wire that is L equal 0.05 meters. In a 1.5 Tesla B field, and the wire, has how many amps? I equal to 20 amps. So it's a big B field, huge, very big, got a lot of current, and a short length. This is designed, we're doing example 22.4, and the diagram is figure 22.30. Okay, so that'll show you exactly what we're looking at. So we're going to use F equals ILB sine theta. Of course, theta is equal to 90 degrees, so this equals 1. Straightforward. Our F is equal to 0.05. We're multiplying that by 20 amps, and we're multiplying that by 1.5 Teslas. These two things combine to be 1. So 1 times 1.5 is 1.5, and we're dealing with newtons. So we've got 1.5 newtons equals our force. It's a lot of newtons. It's a lot of B field is what it really is to get a 1.5 newtons. But that is what happens sometimes. Okay, so we're going to stop here with this video. We've basically gone up to We're going to look next at torque on a current loop and motors. So we're solid for now.